All right, so we might wonder then, well, how are we going to construct this wave equation, which is going to encompass the positive aspects of the Bohr model for the hydrogen atom, but will handle all other atoms and potential energy fields and everything else in the universe. And so Schrodinger is credited with coming up with this wave equation, and it was in a moment of inspiration that he was able to develop this equation. But one of his main goals was to find a wave equation that was consistent with the principle of conservation of energy. And for the moment, although this equation was generalized to quantum field theory by making it consistent with relativity later on, at first he was just interested in a non-relativistic wave equation. The indications were that the electron's motions around a hydrogen atom were non-relativistic, and so that most of the important properties of the system could probably be determined by a non-relativistic solution. And there are some big problems with the relativistic solution that we'll get to later. But we wanted it to be consistent with conservation of energy, and so in other words, total energy equals p squared over 2m, which is kinetic energy, plus potential energy U. We want it to be consistent with that non-relativistic energy equation, where U is our potential energy function. And P is our momentum, mass times velocity. Okay, but we also want the wave function and its derivatives to be smooth and continuous. Okay, and so he started messing around with a lot of different formulations, and he wanted something where somehow you could operate on the wave function with something that would give you the energy equation back again. So you imagine then, well, let's say that we've got a psi wave function that looks like a e to the plus I kx. You might wonder, well, why would we want to go with something like that? B e to the plus I kx. And the answer is, this is really just a sum of sine and cosine functions. Okay, and imaginary complex exponents, that's not obvious that those give rise to sine and cosine functions, but really in a Fourier analysis what we're interested in doing with waves is just adding a bunch of waves together that have sine and cosine properties to them. And so how does that work then with something that looks a little more abstract like this? This is what we could call our spatial dependence. That's time independent. So what do I mean by that? Well, I mean that we're talking about things that all the transients in the system have died down. So it's like a standing wave pattern that would have just a steady state solution that would be the same at all points in time. Now, what I would like to try to show is that this is the same thing as A prime times the cosine of kx plus B prime times the sine of kx. Now you might wonder, well, if this is actually a traveling wave, why am I not writing kx minus omega t? And the answer is, if it's time independent, the time part is going to cancel. Okay, and so I'm just going to cancel it out before I ever get started with it to keep the expression simpler. But we will also look at time dependence a little later on, and I'll show you how to work with that aspect of the Schrodinger equation. But that is a more difficult kind of a problem to work with, and it's more of an upper division kind of a problem. But I'm not completely forgetting about the fact this is a traveling wave, but I'm saying that there's a steady state solution that's time independent. Okay. So De Moivre's theorem shows us that e to the I plus or minus I theta is equal to cosine theta plus or minus I sine theta. So this is a very powerful theorem, and it basically relates this complex exponential to a sum of sine and cosine functions, but it does it by means of imaginary numbers. So here I, of course, is the square root of -1. Okay, and let's say, for example, that we wanted e to the I pi. That would be the cosine of pi plus I sine of pi. Okay, so the sine of pi is 0. So we have here e to the I pi is equal to -1. This is one of the strangest results, I think, in mathematics. That you could have an irrational number raised to this is I pi, sorry, the I pi is -1. So you have an irrational number, e, raised to an imaginary irrational power is equal to an integer. That is so weird. So they've actually come up with some kind of theorems and stuff that have shown that pi must have the properties of a non-transcendental irrational number or something, because a transcendental irrational number raised to another transcendental irrational number power cannot be equal to an integer or something like that. And so they get into all kinds of weird things. But I mean, isn't this strange that we've got this irrational number to an imaginary irrational power is an integer? One of those really weird things. But we can think of this as being a connection between geometry and algebra. And it turns out that this algebraic form of our sum of our sine and cosine functions is easier to use when we are applying the math of the Schrodinger equation. So I just want to talk about this a little bit, and I want to show how these relate to each other. So let me just take this and expand it out and show that it's equal to that. So this is going to be a times the cosine of kx minus I sine of kx plus b times the cosine of kx plus I sine of kx. And then we'll factor out the cosine kx's. So it's a plus b times the cosine of kx plus I times b minus a times the sine of kx, or that's just equal to what I've written here, a prime cosine of kx plus b prime sine of kx. So what I've just shown then is that this formulation is equivalent to a sum of sine and cosine functions. And if we can show that this is true for one value of k, which relates to the wavelength of the k, you'll recall from before, is 2 pi over lambda, so that relates to the momentum of the matter wave. If it's true for one value of lambda, it's true for all of the different values of lambda. So in other words, a sum of these solutions will also be a solution if it's true for any given value of lambda. Okay, so it turns out that this can be given physical significance, and so can that. Let's see how Schrodinger was able to do that. He said, imagine that there's a momentum operator. It's equal to minus I h bar d by dx. Then, if we want to apply that momentum operator to psi, what we're going to end up getting here is minus I h bar times d e to the I kx dx plus d e to the minus I kx dx. Okay, now the derivative of an exponential is just a e to the ax. Okay, so here the a is going to be the ik. For this one, it's going to be a minus ik for that one. So we end up then with minus I h bar times I k e to the I kx minus I k e to the minus I kx. Like that. Okay, and so we end up with here then is I times I is minus 1 times negative 1 is 1. So that gives me h bar k e to the I kx. And then here, we're going to have minus I times minus I. That's going to give me minus 1. That's minus h bar k e to the minus I kx. Now, this is interesting. If we make use of the fact that k is equal to 2 pi over lambda, and h bar is equal to Planck's constant over 2 pi, then that gives us h bar k is equal to 2 pi's are going to cancel. Just h over lambda is equal to p. Okay, so basically what this is giving us then is the momentum p times psi back again. Because this particle is going to correspond to motion in the negative direction. Okay, and so if we look at this, this corresponds then to a particle moving minus x direction. And so by defining the positive direction to be to the right, this is going to be the momentum of that part of the particle, which is moving in the opposite direction. And then this is going to represent then a particle moving in the positive x direction. So are we talking about different particles? Well, not exactly, because here, this could be the same particle that's moving, but then hitting a boundary and bouncing back. So this could be the reflected aspect of this particle, and this could be the just the particle moving in the original direction. So in other words, by applying the p operator to psi, what we end up getting is the momentum times psi back again. And so this is sometimes called an eigenfunction here. This is an eigenfunction. And then we operate on the eigenfunction, and we get an eigenvalue back again. Okay, so there's like an eigenvector and an eigenvalue. And so that's something that you may have heard about in some of your more advanced math classes. But the idea here then is that if we apply this momentum operator to, if we were just, say, looking at a particle that's moving to the right, we get p times that wave function back again. Okay, and so if we took two p ops, then that would be the same thing as two different operations. So p op psi equals p psi. P op squared psi would be p squared psi. Now p squared is getting closer to the kinetic energy, because the kinetic energy is p squared over 2m. And so if we do I h bar d by dx, and we apply that operation twice, what we end up getting is minus h bar squared d squared dx squared for the p squared. Then if we divide that by 2m, then basically what we've got is minus I h bar over 2m d squared psi dx squared equals the kinetic energy times psi back again. Because each of these p operations is giving us a momentum. Now that seems kind of abstract. What is it that's happening when we do an operation on a wave function? Well, physically, we could think of that as being a measurement that we make of the system. And so by applying the momentum operator, we're essentially measuring the system in a way that could give us the momentum back again. And so although this seems very abstract to be taking and applying an operation to the wave function, we could think of that as being p squared over 2m psi, or k psi. Okay, so in other words, Schrodinger was looking at a way to write something that was consistent with the principle of conservation of energy that included a wave function that could be solved as a differential equation for psi. But the only way that this is going to give us different solutions is if we have a different potential energy function. So what we really want to do then is we want to add the kinetic and the potential, and then multiply all three of these terms through by psi. So by making this assumption that p op might equal minus I h bar d by dx, or in the case of a three-dimensional problem, these would be partial derivatives, we could then make this consistent with the energy equation by writing this as minus h bar squared over 2m d squared psi dx squared plus u psi is equal to E psi. Because this part is your kinetic energy times psi, and then this is yet to be determined. This is the potential energy function for whatever system you're in. So this is the potential energy that the particle is subjected to. And then we've got a second order differential equation which can be solved for psi. Okay, so this is the one-dimensional Schrodinger wave equation. And is most easily solved for a one-dimensional particle in a box. So let's do that one, okay, before we go any farther with this. Because we already know the answer to that one, and so let's see if we can get that answer using the Schrodinger equation. Now, because the particle in a box is purely a combination of these different sine functions, it's actually easier to use the sine function formulation. But most of the time, we're going to want to use that exponential formulation. So don't forget about that, because in almost every other example we'll be looking at, other than this more simplified particle in a box explanation, we are going to be using that complex exponential stuff. Okay, so let's assume then that psi is equal to A times the sine of kx plus b times the cosine of kx. Okay, so that's our most general solution, and then we can go through from there and see what parts of this need to be analyzed more carefully. Now, because we have boundary conditions of nodes at the endpoints, this requires then that B coefficient equals 0. And this would be true for all of the different harmonics. So we could write this as an sine knx with bn cosine knx, because we know that there are going to be a whole bunch of solutions. We already saw that was true for our particle in a box problem before, is that there are a whole series of different values for psi that satisfy that equation. And so we just want to show that that solution is consistent with the results that we get from the Schrodinger equation here. And so that would give us confidence that maybe this would work for a more complicated kind of a problem too. And so that's the whole idea of why I introduced the particle in a box problem before we got started with this, so that I can now apply the Schrodinger equation to the particle in a box and show that we get the same results that we got for particle in a box, but with more information thrown in. Okay, so if we plug in that assumed form, then U is 0 inside the box. So this is a particularly easy problem to solve. You can just write this now as minus h bar squared over 2m d by dx squared of A times the sine of knx is equal to En times psi. Okay, because the U is 0 inside of the box, this is basically what we're trying to solve for. And then the psi over here we'll write as an sine kn x. Because that's our psi wave function for the nth harmonic. Okay, so if I take two derivatives of this, what this is going to be equal to then is, well, the first derivative, the derivative of sine is cosine, so it's just going to be k a times the cosine of kx. And so then the second derivative of a sine kx is just d by dx of ka cosine kx. And so that's going to be another factor k is going to come out. And then the derivative of cosine is minus the sine. So this would be minus k squared an sine knx. Okay, so that's our second derivative. So we can write this then as minus h bar squared over 2m. And we have the second derivative, which we just did over there. It's going to be minus k squared an sine knx is equal to en times an sine knx. Now we can see that the wave function itself cancels. And so what we end up getting then is a condition on h bar and k that makes this equation valid. Okay, so what's left then is just h bar squared k squared over 2m equals en. Okay, and so we're going to need to go a little farther with this, using the fact that the boundary conditions are nodes at the endpoints. Lambda n we saw before was 2L over n. So we'll plug that in here. It was h bar squared times 2L over k is 2 pi over lambda, sorry. So that's 2 pi over 2L over n squared over 2m. Or that's equal to the h bar squared and the 2 pi squared are going to cancel. That gives me h squared over, and then there's an n here in the denominator of the denominator. That's squared, so that flips up to the top. And then 2 pi's have canceled from h over 2 pi squared and 2 pi squared. So what's left then is just 8 ml squared. So this was the result we got from before. But it was gotten by solving the Schrodinger equation. Pretty nice, because what that's showing is that the Schrodinger equation is giving us the same answer that we could have obtained with a simpler problem by just more elementary means. Okay, so that's our nth value for the energy. Now what about the wave function itself? Can we go into more detail about what Kn is equal to? Well, Kn is equal to 2 pi over lambda n. So that's 2 pi divided by 2L over n. So that's just equal to n pi over L. So we can rewrite then that psi n is equal to an times the sine of n pi x over L. Okay, so this is the expression then for the wave function of the nth harmonic, and this is an expression for the energy of the nth harmonic gotten from solving the Schrodinger equation for a particle in a box with a 0 value for the potential energy in the width of the box between 0 and L.